Okay, so the way I'm gonna do kind of a review slash overview as well as preview of courses that you would have to take, or maybe one course that you might have to take to actually finish this. Okay, so because we're not done by any stretch of imagination, and one thing is certainly you can see this number over here, that a lot of things we have discussed have been n-dimensional, and that including this part, the line integral is actually entirely n-dimensional, the concept itself. So you can travel through n-dimensional space, and the work makes sense, line integral makes sense, and a lot of analysis that we have done, including the gradient idea, the gradient vector fields, and the fundamental theory for gradient vector, fundamental theory of calculus for gradient vector fields also are correct, but this part we cannot discuss yet in higher dimensions. Okay, so all right, so that's why you need to do more. And the idea then of this kind of review, I'll go over things that are trying to get like a bird's eye view of what we have done and what we could have done and might do at some point. With the references to primarily different dimensions. And there is a way to see everything together as one, and that's the big point here, is that the exposition naturally in a course goes step by step, in logical steps. It's like you're telling a story, but then now it's too late for that. So you are to take a final exam. So it's ideally you have by the time the finalists have kind of big picture, or maybe just one thing like that you hold, and you understand it as a whole. So and incidentally, this formula brings in just about everything that we have talked about writing into one formula. So we have line integral, and we have double integral, and we have a vector fields, and we have parameter curves. So see, the major topics that we have discussed are all here. So all that remains here is just to really bring it to the next level, is to look at what would be this theory look like in the next dimension. So we're going to do that in a minute. So once again, what this kind of fundamental theory in dimension 3 would look like. Okay, so that certainly is an interesting question. But as in the spirit of what I have been doing, it is in fact a good idea to downscale first and make that connection to dimension 1 clearer. Okay, so once again we can proceed to dimension 3 here, but actually we are coming from dimension 1, and so all of these connections have to be made, and then ideally, which is the big deal, is how to see the whole thing as one, not just a kind of different formulas in different dimensions, but there's really one formula. Okay, so what's the picture is here just kind of smallish, so I might want to repeat it to make sure that we are talking about clear what we're talking about. It's a curve that bounds oriented curve bounds a region in on the plane. So this is R2. Okay, so the region, as far as we're concerned, is it could be square, it could be circle, but it's not a ring. Okay, so because if we have a ring, then we cannot, then the boundary will be made of 2 pieces. Okay, so that's a requirement that we have to satisfy. Even though there is a version of Green's theory that I tried to talk about a little bit about yesterday, is for this kind of region, as long as it works out just fine, as long as you understand that the integral on the left is actually might be made of 2 or more curves. Okay, so and it works out just fine. And the big point was that the function itself has to be defined in every point of this region. So if it is an undefined single point, you have to surround it with a curve, and only then the theorem will work. Okay, so let me take this theorem and try to go back and see what it has to do with the fundamental theorem of calculus, the original one. Okay, so I'll take this formula. So all the caveats are still here, still to worry about. But let's just look at the formula and the formula only. So green theorem, dimension, green theorem, fundamental theorem, dimension 1. Technically known as green theorem of calculus, dimension 2. Okay, so let's try to understand and match it with the theorem of in calculus 1. So fundamental theory of calculus, dimension 1. Okay, so I'll let me just write it out and see if there is anything springs to mind. So also let me just ignore this formula and just write the new one. Integral from a to b fx dx equal to f of b minus f of a, the n. Okay, so that is, well, not the n, because we have to also say that p prime, f prime is equal to f. Okay, so one thing I already mentioned last time is the mismatch is that I don't know what to call it. Just try to erase this and okay. All right, so okay, so equal. Okay, so the mismatch is with the terminologies right away is that f capital is actually what we're trying to integrate. What we're trying to integrate is f capital. Okay, so that just in that spirit, it's really not a big deal. Just using different letters. Okay, so that already takes us a bit closer to the truth, to the formula. So calculus 1, we're taking the fundamental formula and trying to see to match it with the dimension 2. Okay, so that is already closer. Let's look at the left-hand side. So I omit the dot. There's no dot in the bottom because these are numbers, so there's no dot product to worry about. But I could put dot here. That would not hurt anyone. What else do I need to do in order to make my left-hand side match? So this one to match that one. What else do I need to do?
Do we need to say something more explicit about the boundary of C?
No, let's just look at the formula. Let's just look at the formula. So C bounds. Hold on a second. Just a minute. Okay. Well, hold on a second. Oh, right. Oh, I was going in the wrong direction. Okay, let me erase this. Yeah, I was looking in the right direction altogether. Okay, so let's start over. Okay. What's wrong with this thing? Okay. Okay. So what I was trying to write here is like I said, as I went in the wrong direction. Yeah, so the mismatch is actually kind of more complex here. It is, let's look at the dimension of the integrals, or the dimension of the space. So the dimension of the space is 2, and then it is 1. But what about the dimensions of the integrals? Okay, so let me erase this. Is kind of irrelevant at this point. Dimensions of the integrals. Dimension or degree, if you like. 2, right? Degree 1, right? Line integral. It is once you carry out the substitution. Remember that you end up with just a typical integral, the same integral as this one. Okay, so that's fine. Now, but the right one, if it doesn't work out this way, you end up with integrating over, say, a rectangle, and it comes from a double Riemann sum, and you remember you divide the rectangle into pieces, so that like this, and that's where it comes from. So degree is 2. The function px, qx, and py is let me make it clear that f is equal to pq. a vector field. And so these are two functions of two variables, and so you integrate two functions of two variables and double integral. Okay, now what about the same question applied to the fundamental theorem? And the original fundamental theorem. Okay, so clearly this is degree 1. What about the right-hand side?
You just call it degree 0?
Degree 0, that's right. This is degree 0. There is no actual integration. Okay, so we are talking about just points. We're talking just about points, and that's what informally you can refer as degree 0 integral. And you could match up the notations with something that we use in calculus 1, and it is f from a to b. It a little bit looks like an integral, and that suggests that that's what we're talking about here. So degree 0, degree 1, and then you realize that if we try to match these two, they actually don't match because they're in the wrong order. So as you can see, the fundamental theorem, original one, goes from degree 1 to degree 0 down, and the one is for degree 1 to degree 2, it goes up. So in order to make this match, let's flip the terms. Okay, so I'm flipping the terms so that I have what I want. So I'll have f with from a to b is equal to single integral from a to b f dx. Okay, so as you can see, the capitalization actually matches pretty well with the Green's theorem at the top. Okay, so once again, then there we have a match that we going down in dimension from dimension 0 or degree rather to degree 1. Okay, degree 1 and degree 0 refers to specifically to those differential forms. Remember the differential forms, that we are not integrating functions in that sense. We're integrating differential forms. What I just talked about yesterday. This is the new notation over here. See, so what we are integrating is this. Where is it? Here it is. This one is integration of. This is the differential form that we integrate. Differential form of degree 1, which looks pretty much the same when dimension goes to 3. Once again, degree, dimension, not the same thing. Degree is the number of variables, x, y, 2. But if you have x, y, but the degree is the dx, how many d's appear. So dx means degree 1. If you have dx, d2, degree 2. Okay, so this is dimension 2, degree 1. This is dimension 2, degree 2. But you can certainly think of, if I could have dimension 3, degree 3. It will have x, y, z, but you cannot have 3 of them simultaneously. You have dx, dy, dy, dz, dz, dx. Okay, so that's where the complexity and cumbersome formulas that you may have seen elsewhere come from. And this one will look much more complicated. In dimension 3, you will have simply the third term like r dz. Okay, so that's what we have seen when we discussed the curl. Remember? So these are the differential forms we're talking about, and they are referring to and pretty much identical to degrees of the polynomial of the integrals. Okay, and then degree 0 is nothing but a function. So when there are no dx's, that's a degree 0. So just like degree dx with d0 degree, what is it? It is 1. Okay, so the differential forms with no dx and dy's is simply a function. So then we start with function at the ground level, then degree 1 differential forms, degree 2 differential forms, and so on. We're climbing these dimensions, but here we are limiting ourselves to dimension 1 and 2, the space of dimension 1 and 2, and you cannot have degree 3 differential forms in dimension 2 because there is no dz, and there can be no triple integral for 1. Okay, so that's we don't have too many differential forms to worry about. Okay, so we are then where we are right now is this, this one, and we're matching up with that. Okay, so we have almost matched entirely. One thing we need to fix is this. So what do we do with the limits? We did it previously, so I wonder if you remember how we would treat this. Integration from A to B, as we will use that language in Calculus 1, language we will use now.
Would we just use, we consider A and B as functions of some other parameter t?
No, it is, what you're thinking about actual parameterization of the curve, and that's what we did yesterday, and that certainly is what's behind either that one or this one. But what I mean is that we do integration, and when we speak of line integral, and that's what I'm trying to accomplish here, I want to turn this into a line integral of dimension 1, except it's not going to be over closed curve, but a regular curve. And what we did is we integrate not from A to B, we integrate over an interval AB, which is, what is it? It's a curve. Okay, so that's how we're doing it, and then you realize that the left-hand side over there matches the right-hand side here, except once again that's kind of crucial part is that that one is over closed curve like this, and this one is naturally integral AB is not a closed curve, but otherwise it's exactly the same. Okay, so that way we have a matchup of what? Of kind of dimensions are matched up. So let me once again do this. So we're matching this formula with that formula, but in different dimensions. And so integral on the left, integral on the right. Degree on the left is one lower than degree on the right. Okay, so these are the two main things that make the match, but certainly there is more to it. And number one is this, and that is, let's look at the relations between, in both these two formulas, the relations between the domain of integration. Okay, so domain of integration in the fundamental theorem at the top, it is C is this boundary of the region D, which is inside. Okay, so do you see what that matches in this formula? What matches that in this formula? D here, C there, C bounds D. What do we have it here? Analog. So,
the endpoints of
yeah. So the endpoints, these A and B are the endpoints of the integral AB. In that sense, they bound it. Okay, so let me try to use the same color. So A and B. Okay, that is what we integrate over on the left. And what do? They bound the integral D. Well, it's not the integral D, but it matches. That's the match between the picture over there and the picture over here. That is one-dimensional picture, that is two-dimensional picture, but the idea is the same. We have some kind of region in dimension 1 or 2, and then the other set in the left-hand side bounds that region. Okay, so this is how it is written. The letter used for the notation used for boundary is this curvy D. So D is equal to C. That's the notation for this picture. The boundary of this region D is C, the curve. So the boundary of this two-dimensional region is the curve C. Okay, same thing I have over here, except the boundary of the integral AB is made just of 2 points, A and B. So it's the same statement. So that provides us with one more matching of pieces of these two formulas. One familiar from a while ago, and the other one is very recent. But things match. Things match. So on left, once again, on left, the original integration on left is the boundary of the original integration on right. Okay, so that's what this indicates. And if you want to write the general integral, then you would a general formula for this, which is called the Stokes formula. Then you would just use that language, and it will be applicable to all dimensions. The one thing that remains to be matched, it is the integrands. So the domain of integration has been matched between the two, and then now how do we match the integrands? And it is hard to match them as functions, but it's easy to match them as differential forms. Well, not easy, but at least the concept is available here. Well, if you just look at this one, the relation between f capital and f lowercase is that f capital, the derivative of f capital is f lowercase. Okay? So that's the relation between the integrands in the original fundamental theorem. Okay? So it is not so easy to see that relation, similar relation in the new theorem, in Green's theorem. But it is in fact pretty much the same case if we talk in terms of differential forms, and that's pretty much what we have to say is that the integrand over there, its derivative will be the integral on the right. So you certainly remember what the integral on the right is. Another notation was the rotor. Okay, so the rotor of f dA. Okay, so let me write it this way. Rotor of f, which is PQ, vector field PQ, and it is equal to, as you can see, it's not equal to, we could interpret this as we interpret it as qx minus py, and it is a function. Okay, so with functions, it's a bit more awkward, but it still makes sense. Then it makes sense, but not in a very satisfying way, because the relation between these two integrands is very straightforward. It is the derivative, period. Okay. However, and here it is. If I take the vector field, the rotor of a vector field is not its derivative. Okay. So remember we talked about derivatives of vector fields. There, the dimension goes up by a lot, and it is remember the vector field is defined on the plane, let's say, so two input variables, and how many output variables? 4. Okay, so the rotor is not the derivative of the vector field, but it is the derivative of that differential form that we see over there. So I'm talking about this p dx plus q dy. Okay, and then what we do is we carry out an operation that is familiar from integration by substitution, calculus 1. So you can think about what here it is. df is equal to f prime dx. Okay, so this is what we did in calculus 1, integration by substitution. Now I am doing the same in dimension 2. Okay, so df is equal to f prime dx. Where is it? I'm sorry, f without prime here. Okay, df is equal to f dx, where f lowercase is the derivative of f capital. Then this idea of which you did when you did integration by substitution reappears here. Look at it, f, and this is df. This whole thing, this differential form over here is df. We're doing the same thing with dimension 2. We are kind of differentiating this differential form, except we have more stuff going on, but the rule still applies exactly the same way. Well, how do you think I'm going to be doing this? following the same ideas over there. So I guess just to refresh your memory, df is equal to f prime dx. Okay, so that's how we did it. Remember, u is equal to x squared, du is equal to 2x dx. This certainly looks familiar, right? So that's what we're trying to do here. This is more complicated because this is actually multiplication. Okay, and how do we differentiate multiplication? Well, first we deal with addition, then we deal with multiplication, and then we will end up with the order. Let me just quickly carry it out. So d p dx plus d q dy, and then I'm applying, what am I applying?
Is there anything to the fact that pdx plus qdy is it's the dot product of?
It is, but I'm not sure if it is. I don't want to do n-dimensional. So the dot product, the notation that I used originally, certainly applies to all dimensions, and that's the advantage, and that's the purpose of it. But here I'm just trying to deal with dimension 2, and when the dimension is 2, then it is what it is. I don't want to reassemble it back. So at some point I took my dot product and expanded into this formula, okay? But yesterday, this time I don't want to reassemble back, and I just want to take this and just differentiate using the rules of differentiation that we know, and we apply the product rule. So I'm going to have dp dx plus p ddx plus dq dy plus q dy. Okay, for whatever reasons, it's a bit too long to explain. Differentiating twice gives me 0. Okay, and for one reason, the differentiation takes the degree of the differential form up by 1 unit, by 1, and since there is no dimension 3, we end up with 0. Okay, so and then this is what I have: p prime, d dy dx. So we're differentiating y with p with respect to y, and then we differentiate q with respect to x. So it will be q prime x dx dy. Okay. And then the last step is to realize that dx dy is not the same as dy dx. What do you think the relation is? Dx dy versus dx dy. Dx dy versus dy dx. What's the difference? Well, think double integrals.
So the way you solve it?
It's the order of things. So either you look at the x-axis first and then y-axis, or first axis then the y-axis. What's the difference? If you integrate a double integral and then you interchange x and y-axis, what's going to happen to the integral?
It'll just change based on if you're solving y or x first.
Right, but you can. There's a specific answer there. It will change, but nothing. Just the sign will change. That's all. So that's the weird thing about it. So it will be negative py prime dx dy plus qx prime dx dy. So I factor it out, and I have qx prime minus py prime dx dy, and this is the order of our vector field PQ and dx dy, and that gives me my once again Green's theorem. Green's theorem, what this is Green's theorem without the integral signs. Okay, so so that's pretty much how it works out. And then you know what to do whenever you have high integrals. You apply the same rules of dealing with differential forms, and once again, everything will just fall into your lap, even though it certainly requires proofs, but at least what needs to be justified is these computations rather than any kind of integration formulas. By the way, I don't want to give you the impression that it's all about, when I speak of integration or differentiation, it's all about as you have noted in Calculus 1, so formulas of differentiation, formulas of integration. All of this can be done with a spreadsheet. Okay, so which we did pretty much yesterday. And remember when we did it one square at a time, and that's what the integral on right is. You can have a grid. So that region over there, D, might be just zoomed out. Region made of nothing but squares, and its boundary will be made of nothing but edges of those squares. So like these are little squares, and then along these squares goes C, and then the shape could be anything you like, and you zoom out, and you will have the loop will be just like that. And then on right will be you simply will be adding values. So integration is simply addition. You're walking over that region, visiting every point in D, and you're adding the values of that function, the order in the parentheses. And then, so that's what happens on the right. And on the left, what happens is you walk around the region and not visiting anything inside. So once again, on the right, you visit every point, every square within the region D. On the other hand, the left is very different. You only visit its boundary, and that's the curve that surrounds the region is made of edges, and you just visit every edge, and once again you do summation, as we did yesterday. Okay? Yeah.
I was wondering, we were talking about how we can't integrate over the domain. Our function has to be continuous over the.
Yeah.
So I know that in Calc 1, if you have if the function is differentiable, well, if it has. Sorry, if we're
if one point is missing, it doesn't matter. That's what you're saying.
Yeah, I was going to say, because that little inner circle can be made arbitrarily small, is that right?
Yeah.
And so its contribution goes to 0?
You would think, but it is not entirely true even in Calculus 1. If the function goes to infinity around that point, you cannot remove that discontinuity and discard that value. So the problem is exactly the same as far as differentiability is concerned. If it is undefined at that point, this the only thing that you know is undefined. Then it means that your right-hand side will be undefined. So this would be undefined. If that function is undefined somewhere in between a, b, this cannot be defined unless you make some other provisions, and such as maybe you say, well, what if the function is, say, has a limit? If it has a limit, then even though it's undefined, then you can that will work out, and the function will be still integrable, right? You add at any point, and it will be integral. But in general, it's not the case, and so it could be then unless you say that there is some special condition on the function f. You cannot proceed from left to right. So here on left is just two values, so nothing that can happen. Same thing with the line integral over there. It doesn't matter what's happening in between, inside of the region. You only visit the boundary. But if you want to transition in this fundamental way from left to right, then you do go over the whole region. And then if there are some the function, whatever you produce function over here is undefined, then you're in trouble. The formula simply doesn't work. So these are just bare bones formulas, and I do not put here all the caveats that we usually do. And I did with respect to that one. In Calculus 1, you also certainly remember that there is a restriction on the function, on this function. It is required to be integrable. So if and you cannot make an integrable function if it, say, goes to infinity. Okay, so it's similar in the situation that we encounter. Remember that rotation vector field that when it is divided by x magnitude squared, it has exactly that behavior it has in the middle. It goes to infinity. The magnitudes of vectors go to infinity, and so you cannot even fix it. If there's only one point missing, we know it's called removable discontinuity. You put a point there, and it will work out just fine for integration purposes. But if it goes to infinity, you cannot fix it. Okay, so as I was saying, the computation can be done with a spreadsheet, and what's however also interesting is the idea that is hardly obvious. It is how you can compute. We have used double integrals to compute areas, and so it turns out that you can compute the area without visiting every point. So if you remember the definition of the double integral, it is like a region like over there. You divide it into little pieces, you compute the function, and then if that function is equal to 1, so imagine that what's in parentheses over here is equal to 1, right? So if this is equal to 1 by some accident, then the integral will be equal to the area of D, right? So when you integrate 1, you end up with the area of that region. However, if we go now to the left, then we are computing the same area, but not without visiting every point of the region, but rather making a trip around it. Okay, it's like the idea is when you need, say, to compute the area of a region that you have no access to. It could be maybe fortification. You are laying siege to a town. You cannot get in, and you want to know its area. How? You just take a trip around it, apply Green's theorem, and you will know its area. Or maybe there's a pond, so once again, you cannot walk around to map it entirely. So what do? You make a trip around and carry out this integration. The only thing remains is just to determine what should be your vector field, and I think I could tell you it will be, what is it, y0. Is that right? Yeah. So if my vector field is y0, then qx is 0, and py is minus here, right? And py is -1. This is a minus. This is a minus. So -1, 0. So then py will be 1. Py will be -1. So altogether, my integrand on the right will be 1. And indeed, so my line integral of this kind of special vector field that I have over there will will give me the area of that region. So once again, taking a trip around this pond in doing these computations, line integral, will give me the area of the pond. Okay, so that idea certainly is nowhere visible in here, even though you probably can produce an analog if you try. So it's like, how do I compute the length of the integral AB without visiting every point between A and B? Well, you just integrate a function that is appropriate. What would be that function? What?
What was the question? Sorry.
How do I use this formula to compute the length of AB, which is actually B minus A? So that's the length of integral AB. I'm trying to have an analog of that observation that you just made about how we can compute the areas by line integrals. And here we can compute lengths by no integration at all. And the answer is, well, you have to appropriately pick the functions, and it appears to be, it should be equal to 1. So f is equal to x. Okay? So if I integrate x over integral AB, the integral will be equal to b minus a. We know, we have known that. Okay, so the time is running out. So at least I should mention about as I meant from the beginning is what happens in dimension 3. So we have an analog between dimension 1 and dimension 2, and now if we ascend to dimension 3, let's at least try to imagine what's going to happen. Okay, so let me copy this. Okay, so this is my standard integral. Green's theorem, two-dimensional. This is my two-dimensional fundamental theorem. Okay, now here what I want to do in the remaining time is to create best I can an analog for for dimension 3. Dimension 2, dimension 3. So you can imagine that all the dimension will go up. All the dimension will go up by 1. So here I'll have dimension 2, and here I'll have dimension 3, which means that I'm going to have here double integral, and here we'll have triple integral. Okay? The trouble, let's look at the right-hand side first. First of all, what do I do with that a over here? I replace it with v. Okay, so this is a volume integral then. Okay, I'm not going to be trying to comment about I'm going to have here. It's just a bit complicated, so I'll just kind of hide it to be figured out. Now, what's happening and so this is a three-dimensional region. We're talking about some kind of integrating some function of 3 variables of that region, and that is what we have on right. What's on left? What do we have on left? So it's a double integral. Okay, so what do you think this is about? What kind of double integrals do we know? Actually, we don't know appropriate double integrals because well, why not? We do know double integrals, but that's not the double integral that we know. Why? Because look at this circle over here. We would have to be talking about, just like we talked about over there, about this indicate closed curve. So here it indicates closed surface. Okay, so region, three-dimensional region D, it is bounded by a surface. So D is inside, and on the outside, this one, this thing, that is C, not C, but, well, it could be just, how about S? Okay, so it's a surface that bounds it. Okay, so that requires development of the surface integrals. And before that, development of surfaces, parametric surfaces. The theory of parametric surfaces, just like, which is pretty much equivalent to the theory of parametric curves that we started with. The difference is not humongous, but it's certainly more challenging. And the bigger challenge is how easy it was to think about parametric curves as paths of motion. So we're moving and then along some road. So either we're studying the road or we're studying the motion. Doesn't matter. The analog from real life is so obvious that it's very convenient and really something tangible to use over there. Now imagine surfaces. How do you parameterize surfaces? So what would be the analog, you think? So you cannot have time with 2 dimensions. Okay, so this was time as we were moving along the curve. We would mark our points and that created a curve. Well, time is not 2-dimensional, it's 1-dimensional, presumably. So we cannot use that analog. Can you think of anything else?
Would we parameterize it by the curves that, like intersections of a plane with the surface, or with the
You can have a bunch of parametric curves. So we in one direction and the other direction. Indeed, so the idea is indeed that it's as if you're traveling in that direction and that direction, and then you create a bunch of curves that intersect in each other on your plane. So this is the plane. But now, the punchline, what does it look like? Does it remind you of anything? What is this very bad picture of? What? It is what kind of sphere? Not just any sphere. The globe, this is the Earth, and I'm talking about maps. So a map would be a good analog for a parametric surface. Okay, so I'll stop here. So so let me know if you need to talk about one. All right, thank you. See you Monday.